Hi, welcome back. I just noticed there's a post on the forum from Scott about Mode 7, looking for help. And in the time I saw the post and came back, Steve's already answered the question. So let's just ignore that. So let's pretend he hasn't. Anyway, so Scott's asking about, can someone show me how to buffer our textures and read them because it's screwing up the rendered output? So I've loaded this into PlayBASIC by the magic of television. And we'll have a look at what the program's doing. It's pretty simple. Hit F5. Yeah, well, you've got, okay. So we're setting up the screen mode, loading a texture, okay, drawing it to the screen for some reason. Locking the screen buffer, grabbing a point, computing the Z for the vertical row, for the column, yeah, for the row of x coordinates, clipping it for some reason here, scaling it, and wrapping it inside this texture size, whatever this texture 1 image was. Just have a look at that texture. So texture 1 JPEG is what he's loading. Folder here, which is that folder there, is it? Oh, it's a big grid. Of course, it's a big grid. Should have known that. Well, you could probably draw the grid in code and save yourself that, but you know, who cares? All right, so back to here. Inner loop. Well, the problem is it's as you already know, he's reading from the screen and writing to the screen. So to have a texture, read from a texture, what you would normally do is, well, what I would normally do is store that somewhere else. There's a few ways of doing that, and I think we'll explore a few here. We won't try and get too low level. We'll try and just modify what we've got here and keep it doing the same thing. So the first thing I notice is that we've got a point instruction and a dot. Now, if the buffer is locked and you are always drawing to what's called the legal pixel, you know that this pixel is inside the bounds of that image. In other words, you're never reading outside the image. Then you can use the fast point alternatives. So we could go, fast dot down the bottom there. The other thing that's unnecessary is we're setting the ink color. Now fast dot actually wants the color itself, so we can just go color. This won't fix our problem, but we're doing the same thing, but why is it displaced 256? Let's run it and find out. That would crash because this is being clipped. Oh, I see. So he's storing the texture on the left-hand side of the screen, and then drawing to the output. To do that, we would have to clip this loop up here by the width of that texture. So this should be okay now. Shouldn't crash. Yeah, but it won't work. Look, what he's talking about is doing a buffer. So what you can do is you can, change the surface. You could go, render to image, and this is image 1. Read the pixel, render to image, and then back to image 0, which is actually the screen. Or you can just go, render to screen. And that's an okay, workaround. But we're changing surfaces all the time. We have to lock these buffers, unlock them. It's very messy. So a better approach really is to run through the image up front and store the pixels somewhere else. And we'll do that up here. So we'll load our image into slot 1. We'll draw it here. We'll make an array. Call it texture, and it's 2-dimensional, so we'll get I'm going to need those multiple times, so we'll call it IW for image width, get image width of image number 1, IH for image height, so alright, get image height. So our array will be an emulation of this texture. It's a 2-dimensional array. We could store it as a 1-dimensional array. I'll get to that hopefully later, and the reasons why you probably should store it like that. But for now, this is the simplest way of doing this thing. So we'll tell the render to image 1. I have X loop to image width -1. Should have done Y loop there, but just have a nested loop running through every pixel in this source image. Y loop to image height -1. Now it's -1 because we're going from 0 across to the furthest first pixel on either the row or the column. Now, when an image is 100 pixels wide, it has legal coordinates of, it has an inclusive exclusive rule. And this is very common in graphics programming in general. In fact, I think it's basically a standard. I've never seen anything work outside of this. So the left hand side is inclusive and the right hand side is exclusive. So we're ranging from 0 to the number of pixels -1. So if you're drawing to pixel 100 on a 100 pixel wide image, that would be actually off the image altogether. It would be on the next pixel after that row. Same with the height. Here we'll go X loop, Y loop equals just whatever the color value is at X loop and Y loop. So what have we got? We've got our width, height, I've got an array to hold this data. We change rendering to that surface. And we'll change it back now to the original surface. And normally, I would suggest that you preserve the surface. There's a command where you ask PB what the current surface is. So if you ever change the rendering surface, then you restore it back to what it was before. So if your code's in a function, you call this from inside your game or your program, and then after it returns, if it changes the current rendering state, the code that was calling this function you've written might actually cause that to behave incorrectly. So far we've done nothing. We'll load this thing into memory, store it up there. Grabbed our points. We don't really need to plot that on screen, do we? The texture itself, I wouldn't have thought so. So down here, all we have to do is we have to substitute the point command here for the texture, the array. It should pretty much do the same thing. Can't guarantee it, but give it a go anyway. And there we have it. We are rendering our classic sort of mode 7 perspective scene. Pretty cool. Okay, we've proven that this is an approach we can use. We can buffer up the texture the source texture into an array, and we can read the pixels out from that array. As long as we don't step outside the array's dimensions, we are okay. And that's what this modulus here is doing. Now what I suspect, I'm not sure, but I suspect that image is a power of 2. Actually, before we get to power of 2, what we might do is we might put this into a loop. Let's have just a do loop here. We'll have a bit of a standard clear screen in front of that. We'll have a loop and a space key or something like that. So if we hit space key, we'll exit out. And we'll dump out a speed, just FPS. Get a rough idea of how many frames per second my laptop can draw that at. Quick save, F5 to run it. We're saying about, I would say about 20 frames per second up there in the top corner here. It's going to vary a bit because you've got a lot of other system stuff going on at the same time. You can't stop Windows from stopping your process and then doing something else. That's pretty good actually. That's better than I thought it was going to run. Can we improve that? Well, I think we can do some obvious things to it. Now, if we do some stuff like this, we aren't actually saving ourselves any time. We can do that in one line. It's easier to read, okay. But we're not winning back anything worth writing home about. That's okay. The benefits are going to be things like, if you look at this loop we're processing through every pixel on the screen. That means this inner loop here, we're drawing every pixel on the screen individually. So these calculations here matter. What we do, every pixel matters. And calling this function every time for an image that's never going to change size is not great. Let's pull it out. So I'll just grab that out there and I'll substitute it with the IW variable. Put this at the top of this loop here. Even though it's actually was used earlier, I'll put that into a function in a minute. We'll do the same thing for the width. So we'll have height of our texture. You have to assume they're going to be square anyway. So we can go that's the image height. So we're wrapping the Y, the row, with inside the legal limits of the texture. Doing the same thing down here for the X coordinates as we plot them. Quick run again to make sure we haven't destroyed anything. Looks like we've got to about 30 frames per second. I think we're bouncing between about 25 and 30. So just by pulling out function call out, because before, if we're drawing, a million pixels and we're calling out function a million times for no reason whatsoever. This modulus here, traditionally these effects are done with a square texture. The buffer is always it's always the same size and it's always a power of 2. Now I'll bet this texture, this up here that we loaded up front, was a power of 2. I better go check that. Properties, details, thanks. That's kind of weird. It's not a power of 2. What we should do is should have this texture here be square, so it would either be a common size for this stuff would either be 256 by 256 or 512 by 512 or 1024 by 1024. One of the benefits of having a texture that size is that we can get rid of the modulus. In PB, modulus is a floating point operation. So So what we did up here, if we actually said to it, since I know that texture now is bigger than what we actually need, and we'll probably get some weird wrapping here, depending on how big those bands are in that image. We'll say image width is 512 and image height is 512. We just run it to make sure we haven't killed it. We haven't killed it, which is good. And we'll have an image width mask. This will be image width -1. And we'll look at why we need that in a second. I'll just print that to the console as a binary version of itself, image width. Is that the right value? Yes. F7 to run here. It's forgotten its positions. Across the console, and we're spewing this out all the time. So see how we've got all the bottom bits there are set, that's what we wanted. It should be the bottom nine bits. Now, what that means is we can use a bit of binary logic to do the same thing, which is all integer. New x equals, what's just new x, isn't it? We can do a mask of image width mask. This will wrap the texture. So no floating points are involved in this whatsoever. Let's pray. See if it works. Who knows? Wow, it worked. I mean, performance-wise, we're about the same. I think we're a little bit quicker. But we're going to bounce a bit because there's lots of other stuff going on. The most important part of that is that we've got a purely integer operation inside this inner loop. I suspect got integer scale going on there. You could have this kind of scale in there. You could do the scaling down here, multiply by that. I'm not quite sure why we're clipping that thing there as well. Because we're actually wrapping this new value here after it's scaled. Let's assume we don't need that. Yeah, let's be brave. And we don't. Now we're getting, wow, almost mid-30s to almost 40 frames per second. That's pretty cool. Given that we're just running through a PB interpreter, plotting out some pixels. Is that as fast as you can get it? Well, no, it's not. To make it quicker, there's some sort of obvious ways to do this kind of stuff. Is that you might not be aware that there's actually a couple of fast dot commands. There's fast dot 2, which draws 2 pixels side by side. The beauty of that is that you could have 50% less loops to draw the same scene. And then you'd have half as many of these calls. Before we butcher that together, before we do that, let's just say that's all we need for our loop. Yeah, okay. Now I haven't bothered doing the mask on the Y. The only reason is that the frequency of that is much less. We're doing it, what was the screen height? 600 pixels. So we're doing that mask 600 times, whereas the X mask was done 800 times 600. A lot. Same goes for these 4X clips. We were looping through and doing every single pixel. Now what you could do, this is going to horrify people, terrify people in fact actually. If you know that the width is an even width for the screen, you might have heard me talk in the past about render routines for drawing graphics, and one of the reasons why the libraries for drawing graphics are so large is that there are many different render routines to handle different circumstances. So images that are an even number of pixels wide have their own version. Images that have a power of 2 have their own version. Images that are 32-bit, 24-bit, 16-bit, etc. There are other ones that do translations between different bit depths. Just as copying an image from one service to another, there's a whole bunch of code to move that stuff around. To make it, like, really, you could just have, in PB, we could just have something like this loop up the top there. In PB code, conceptually, it's just a for next loop, a nested for next loop. We're reading a point from here and writing it to somewhere else. That's all we're really doing, but that's a simple concept, but it's very slow implementation. What we could do is we could do half as much looping. Call this one the original. Original version. I'll make a mess of it. Now, what if we had a version that draws a pair of pixels? Paired version. We can have the same loop here, and we would do a bit of a trick, I guess you might say it as. We want to read from the texture. We want to compute this first pixel from the texture. So I'll call it just color 1. We're going to write this later, and then here we want to compute the second one of these, color 2, and we'll just do a bit of a chump here. We'll go +1. So when we're drawing, we'll draw a pair of pixels. We'll draw color 1 and then color 2. We could just put texture for the second one there. I haven't tested this, so this might be a bit of a shock as to if it works or not. But we also need to do step every second pixel. So we're doing 50% less loops. We've avoided one function call, but we have added one extra operation here. So hopefully the less loop overhead and calling that dot function less is going to be okay. I don't know. And it still runs. And we're breaking into the 44. That was the peak there, 44 frames per second. So we haven't changed the routine. We've just got a version of the routine that's a little more streamlined. And I suspect if we unroll this a bit further, if we unroll it to four pixels at a time, we'll probably get about the peak throughput of what we can do with this for this version of it. Same principle. We're going to read the next one here. You might have guessed there's a version of fast dot that renders 4 pixels in a row. We'll step X across there, so we're rendering that one there. Now you've probably seen a pattern developing here. All right, fast dot 4. Color 3, color 4. Same as before, we've reduced our loop overhead. We're doing a quarter of the number of loops, so we're pixels while iterating through doing a for next loop, 600 times by 800 divided by 4. So about 200 loops times that. So that's a lot of less loops, which means a lot of less loop clipping, etc. But we have added these additions in their place, but we have removed another pair of function calls in its place. got the right pixels. We've got x, we've got x plus 1, x plus 2, x plus 3. Yeah, it looks okay to me. Are we blown it up? No, we're running up to 48, somewhere in the 40 frames per second consistently now. It's pretty good. Pretty happy with that. And we're not, the display is not significantly different, so that's what we wanted. That's what optimization was really all about. It's picking your way through. Now, before I mentioned you could do this stuff with a texture with one-dimensional array. Now, you might want to do that because if we're only ever reading from a particular row on the texture, if we're never reading from an arbitrary sort of line, if we're always reading from one row of pixels on the texture, we could store this, well, a couple of different ways, I guess. To do this, we might just go back to the bare bones version, and we would have to modify the 4 versions of this to make this work. This is the quad version, quad pixel version. You probably notice there's some things we might be able to modify within that loop, but I'll leave that up to you to work them out. All right, back to the original version. This is the original 2D array version. It might actually be more efficient, this sounds crazy, to copy a row of pixels from the two-dimensional array up here, like actually every time we want to do this. We'll try that. So we'll dimension a thing called pixel row, pixel buffer, and we'll make this thing, big enough that we don't have to worry about its size. And we'll just go, it's like 10,000 pixels in size. We don't care about size. We're only going to be copying strips of this texture out into the bottom pixels, bottom parts of this array. We're going to do that with a little known feature of PB. Let's copy array cells. I'm going to go from texture. Now, a source element here. We need texture. We need, it's going to be pixel 0 on that row. We want new Y. You might be thinking, what's the weird square brackets he's using? These are an old feature for computing, for telling it to compute the location within an array as a unique offset for these kind of functions to work. Go back to here. And the delta here, we want this to be 1 pixel. So when we compute that source location for this text, we want it to step in this direction. I should actually give this delta, since it's a two-dimensional array, we're going to give it in array coordinates. So I want it to step 1 pixel to the right, but nothing in vertically. I hope this still works. Actually, I'm using 165, and who knows whether this is actually going to still be working. Destination is going to be pixel buffer. What? Now, because this pixel buffer is one-dimensional, I can just give it pixel 0, and I want it to step in 1 pixel increments, and I want to use the image width for the number of pixels we're copying. Quick cheeky save. Have we got the syntax right? First of all, we do have the syntax right, so that seems to be okay. Let's have a quick look inside that array just to make sure we're getting some data into it. Hit stop, variable. pixel buffer, wasn't it? There we go. Looks like it's working. We're getting a row of whites. I know that's color white, by the way, and 0 is color black. So, and it hasn't really changed the performance that much. Because before, when we were doing, we're back to the 1D version of the routine. We're running about 29. Yeah, something about 30 frames per second. Okay. So now we have that row in where we're reading all of these pixels from the source texture, right? What we can do is we can substitute this one here out for that. This is the pixel buffer, and the reason why this is useful is two-dimensional arrays have clipping in them, and it's quite a mouthful for the runtime to do it. I'm not saying we're going to win back heaps of performance, but we might get a bit of a boost just for storing the buffer in a different way. Try and run it again. Okay, we're getting a few highlights there, maybe a couple of frames per second out of that, but we are doing it's doing a lot more work. But the good news about that is we haven't changed the behavior of that at all. Now what we could do is store the whole texture in a one-dimensional array, and then rather than when we compute the coordinate here, we could actually have the row offset and just be adding the X onto the row offset there. We are adding, one extra addition per pixel, but we are getting away or removing the need to clip this buffer or every time we access it. When PB reads from an array, it does a lot of please and thank yous from this kind of stuff. If I was writing this to be the most efficient version of this routine, I would not do it this way. I would get it pointed to the buffer, I would read the memory directly, and I would write the memory directly. So even though you can do that in PB, you're still running that through the interpreter. But if your intent was to build a DLL of this via PB to DLL, then absolutely that's the way you should go. And there's a few demos of that I wrote when I was writing that tool. One that does this exact same basic idea. It was used, I think it's in a Z rotator or something like that. Does the Z rotation, warping, zooming, mirrored textures, all that kind of stuff. Whether it is now, I have no idea. Don't ask me. Hopefully it's still on the boards. Hopefully it is. Alright, so to make it more optimal, just looking at what we've got here, if you know the scaling of the particular row, right? Do you know how much scaling is being applied to something, or how similar these rows are going to be? You probably could do away with this completely and have a table that represents the scaling and perspective part. So you've got a list of these offsets, and then you're just running through the offsets and then dynamically shifting them based on where you are in the texture, like a shift offset. I know that most classic effects, or if you've ever seen these effects done on old computers, they're particularly stuff like Amigas and Atari STs, this kind of stuff. To do those effects, the code is unrolled to do it fast. It's a shame in PBO we haven't got a read and write point that are well, we probably need a point that does automatic masking or takes the modulus of the input value. Like that would be kind of comfortable. It would mean that you can sort of write routines and just kind of give it a point somewhere and just returns a value, which is pretty handy. It wouldn't be super fast, but it would make sure that you don't have to do this masking yourself. When you shift things into the internal command set to do those arbitrary things, generally you get a better throughput. And the other one was, I've always thought that we should actually have, rather than the way dot works here, some of my own personal libraries that you set the pen, when you add points to, or you draw the next point in a queue, or to the right of it, I should say. You have a function where you would go, set the pen at the start, the left-hand coordinate. I'll run the program again, actually. For each row, you'd set the pen to the start of the row, and every time you draw it, you were rendering a dot, it would automatically step the next X coordinate across to the next one. So every time you call it, you would be drawing across the row for you. Now what that does is it means that you don't have to feed it this X coordinate all the time. Just, you have to give it a point at the start of the row. So you don't have to compute these values all the time, which means that you can get away with what we have to have down at the bottom here. See, we're offsetting from X. We can actually just add to X here, which is the same thing, and we never have to care about what dots we're drawing to. Here I've had to use addition with X inside the expression, not wanting to change X. We could just do that and do away with it. That's actually pretty convenient for you drawing strip kind of routines. It wouldn't be super fast. There's a limit to how much of this stuff we can get done, but it does actually simplify these kind of routines for you. Anything that can take away a few instructions from your PB code, and they can have huge impacts on the performance of your routine. As I was saying before about, if you can, for any instruction in here that you can move out of this loop, then you're winning, you're winning time back. The classic unroll thing I was hinting at before is that this would be the naive version of the loop. This would be the starting point, and once you've got your calculations down, I'm guessing you probably can set this up in a different way to do the same result. Referencing back to old 16-bit, 32-bit computers, those routines have no divides, no multiplications in them, because a division is very expensive, and a mult on those old chips is like 50 cycles. You've only got a few hundred cycles per scan line. So if I do a divide per pixel, I can only draw a few pixels per scan line. And if you need to draw a full screen width of them, that's just not going to cut it. So I'm hinting at that there's other ways of doing the same thing. Anyway, hopefully this has given you some ideas about how you would use a texture and then render from the texture, and possibly some tricks and tips in there, tucked away in there somewhere, and made you aware of some stuff that's in PB already, like fast.2, etc. The reason they're called fast dot, by the way, is they don't have clipping. If you give them coordinates that are outside of the screen you're trying to draw to, it will crash. If I just had these as dot, now dot uses clipping, dot is reactive to things like the capture, change of surface kind of stuff, whereas fast dot is not. Fast dot is just connected to the current surface. In fact, you almost have to physically seed it to the current surface, which is what this command up here is doing. It's sort of making sure that the current surface is held within PB's internal little buffer of what the current surface is, which is some sort of weird, change of behaviour that appeared. I mean, who knows now? 5, 10 years, 20. I mean, I have no idea. It never used to do that, but over time, when that command's been leaned, it's been optimized at some point, and the demos that was optimized with, they still worked, but those other ones where you have problems where you need to see this point up front. Anything where you need a locked buffer and using a fast dot, fast point, make sure you read a pixel up front, or you can actually just draw a dot as well. It's the same thing. But if you read a pixel from that surface, it's non-destructive. That's why I use read pixel. If I draw a dot to a surface, then I'm changing a pixel on that surface. Anyway, best of luck with this. Looks pretty cool, and hopefully I've given you ideas. Getting to if we were talking about raw memory access, we would have copy the image into memory, get a pointer directly to this image up here, wherever it was loaded somewhere, and make sure the image is a power of 2, and we would do all integer math internally. And this loop here, I would probably unroll this to 6 or 8 pixels or longer if I had to. So what we're trying to do there is we're trying to reduce the overhead from looping and just have as much brute force calculation, and the VM spending its time rendering pixels, not doing loops. That's what we're doing here. Anyway, that's enough for me. Thanks for listening, and I'll see you later.